Hello everybody, thank you for joining us today. You are part of the 200 people worldwide who registered to this webcast, powered by Yole Développement, System Plus Consulting, and Nomade. This webcast is entitled First Milestone for GaN Power Devices. My name is David Jordan, and I'm Global Sales Support and Coordination Manager for Yole Développement. So before starting the webcast, let me give you some practical information. First, you have the possibility to submit questions during all the webcast. Just use the Ask a Question window at the bottom of the screen. We will answer as many questions as we can at the end of the webcast, and for the remaining ones, we will follow up with you via email. Also, please note that the presentations are already available and they can be downloaded from the resources section of the platform. Finally, you will receive tomorrow an email with the link to the recorded webcast session. So, let's start with SG Dogmas, Technology and Market Analyst, Compound Semiconductors and Emerging Materials at Yole Développement. SG, the floor is yours.
Thank you for the nice introduction, David. So good morning or good evening, everybody. So welcome to our webcast on GaN power market, technology and patent analysis. So it's a pleasure for me to co-animate this webcast with my colleagues from our sister companies, System Plus Consulting and Nomade. So let me first start with a brief introduction of Yole Développement. I think many of you are already familiar with our company. So we are a market research and consulting company specialized in three main domains, and from photonics, sensing, semiconductor software, and power and wireless, in which we cover RF devices and technologies, compound semiconductor and emerging materials, and then the power electronics, and as well as the batteries and the energy management. And me, I'm part of the compound semiconductor activity, and I would like to show you in this slide the materials that we cover. So in our activity, we focus on both the established and the emerging compound semiconductor substrates that we see here. The established ones would include, as you know, the most mature compound semiconductor gallium arsenide, then the narrow band indium phosphide, and the wide band gaps silicon carbide and gallium nitride, which is grown on several substrates such as silicon carbide, or sapphire. And we will also keep an eye and, of course, track the emerging semiconductor substrates such as the bulk GaN, the gallium oxide, diamond, and engineered substrates on which we see a great interest from the industry over the last years. So we can really say that these compound semiconductor materials are in the core of all the emerging devices that you see around, and they are deployed in numerous end applications, from the consumer, mobile, to automotive, to an industrial applications, as well as the defense and medical market segments. And at Yole, of course, each of these emerging and applicative markets related to photonics, sensors, LEDs, power, and RF are tracked. And in our compound semiconductor activity, we bring a perspective on the markets and the technology trends and analyze the value chain at the substrate, epi wafer, and the device level. So amongst all these interesting applicative markets and also the compound semiconductors, today we will focus on the GaN-based power electronic market. So before jumping to GaN, let me give you some insights on the global power electronic market trends. So over the last years, we have all seen a penetration of new emerging applications, which are boosted, as you know, by several megatrends, such as the climate change or digitalization or mobility, but also some governmental subventions. So we have all witnessed the emergence of new segments, such as the electric vehicles, hybrid electric vehicles, also the charging infrastructures, some sensing functionalities such as LiDAR, the wireless charging for the phone, or some more efficient power supplies to be used in the data centers. So to meet the requirements of all these markets in terms of efficiency, cost competitiveness, and integration, the wide bandgap materials such as silicon carbide and GaN have become a great interest owing to their intrinsic properties. And over the last years, we have also seen remarkable developments in reliability, manufacturing, and supply chain aspects. So now let's see where gallium nitride is positioned in the power electronic market, where historically, as you would know, the silicon-based devices such as the IGBTs and the MOSFETs are dominating. So with the need for smaller and higher efficiency and also lower cost systems, the wide band gaps SiC and GaN have emerged over the time. So we can say that GaN has a really ideal spot for high frequency power applications, competing with the silicon MOSFETs from 50 to 650 volt range. And at higher power, we also see a competition with the silicon carbide. But we can say today that the GaN power market is dominating more on the low voltage electronics of, let's say, less than 900 volts, where the total addressable market is very huge. But then you will ask me, so what is the status of GaN today? So we can see that in this slide, compared to silicon, the GaN development timeline is quite recent. So in early 2000s, we see the first commercial GaN HEMTs from the key fabless players such as EPC, Transform, GaN Systems, Hexagon, Navitas, and many others. And these fabless players partner with well-established foundries such as TSMC, Epicil, and XFAB. And in parallel, many established discrete and power module manufacturers such as Panasonic, Infineon, onsemi, but also well-known power management players such as Alpha and Omega, Semiconductor, Texas Instruments, Dialog, and very recently, last year, Power Integrations have entered the GaN business. So we can really say that almost all of these key power electronic players are developing and getting ready in terms of their product portfolio as the market starts to grow. So what are the applicative market segments for GaN? So here we see some different market segments targeted by the GaN devices. So first of all, we will have the industrial markets such as the UPS, data center, or some photovoltaic inverters, but also the automotive, the EV, HEV, which are, let's say, more conservative markets requiring long qualification cycles and high efficiency and also long-term reliability. And then we see the consumer market where the performance and the cost are driving. So the GaN devices would need these two parameters for a nice adoption. And finally, we have the emerging markets such as LiDAR, wireless charging, or envelope tracking, where the GaN adoption is more in the second place. So the adoption of these market segments are important to watch. So if we come back to the GaN company timeline and superpose the commercial products, including GaN, we have such a picture. So we see that over the last years, the market adoption of GaN devices have accelerated mainly in the power supply market. So by 2018, the major power supply application of GaN is more in the data centers, where the benefit of GaN is really the high power density and high efficiency. So it offers reduction in the overall system size, but also the cost. And the data centers, we see adoption of both 650 volt GaN for PFC from players such as Infineon, Transform, GaN Systems, and also at lower voltage 48 volt DC-DC converter solutions from players such as EPC, Texas Instruments, and GaN Systems. On the other hand, since the beginning of this year, we see actually a great market traction for the GaN-based fast chargers. So we have seen more than, let's say, 50 fast charging brands deploying GaN devices, such as Anker, Ravpower, or Bezos, and many more. And in addition, in Q4 2019, mobile phone manufacturers such as Samsung and Xiaomi have also launched some GaN-based accessory fast chargers. So it's about 45 watts power rating. And here I call this type of chargers aftermarket fast chargers, so which would represent a secondary market opportunity in the smartphone industry. But this is not all. So in Q4 2019, there was also a launch of the inbox fast charger using GaN transistors from the Chinese smartphone maker Oppo. So it means that the GaN-based charger is sold with the smartphone itself, so it really opens the door for a high-volume market opportunity. So let's understand what is the fast charging. So as you know, over the last years, with the arrival of new functionalities, such as the augmented reality, virtual reality, or high-quality games, additional cameras, and of course the increasing screen size, the smartphone battery capacity had to be increased. However, a larger battery means also longer charging time, so which is a trouble from customer point of view. Thus, reducing the charging time has become a crucial parameter for the OEM. So we see each OEM, they are developing their own high power and faster charging protocol, and they are keeping on developing the technology with higher speed. And at this point, the Chinese OEM, Oppo, has adopted GaN fast chargers, so which can enable 65 watts in its new flagship models. And here, GaN transistors can enable really high power density, high efficiency, and also small size, which are the key parameters for compactness and also low weight. And here we have a record charging time of around 30 minutes. So the GaN device used in these chargers comes from power integrations, system and package solutions, where GaNon Sapphire HEMT is integrated with some silicon drivers, as it will be explained more in detail in the next presentation from Elena. So now let's ask the question. So what all these great news will bring to the GaN power market? So as of today, in our understanding, the technology choice depends on many factors. The technology choice, of course, for the converter used in the fast charger. So it can be the power rating, the cost, the desired form factor, and of course the OEM strategy. So while below 30 watts, many of the in-box fast chargers have silicon MOSFETs. Above 30 watts, we see a great competition between the GaN and silicon in terms of cost, small form factor, and performance. So in our market estimation, in the nominal case, we expect more and more challenger smartphone OEMs to adopt GaN. So what I mean with the challengers OEMs would be the Oppo, Vivo, Xiaomi, Redmi. These are Chinese OEMs who really desire to get some market shares from the leading players, such as Apple, Samsung, or Huawei, in the luxury phone, smartphone segment. So one way to do so is really to differentiate their products by launching innovative and high-performance solutions. So as is in the case in the fast charging, so Oppo's adoption is really a perfect example for this. And similarly, Xiaomi has also announced 66-watt fast chargers, and Vivo has also announced beyond 100-watt charging, where GaN is more likely to be deployed in terms of interesting price and performance ratio. So as a consequence, we expect the overall market to reach beyond $350 million by 2024. But let's don't forget that the leading OEM Samsung has also adopted GaN-based devices in its accessory chargers for 45 watts. So we can understand that the OEM wants to really try out this new product and see its market acceptance through its customers. So this adoption can be considered as a really positive sign for the eventual adoption in the inbox chargers. So in our best case scenario, which expects the market value beyond $750 million in 2024, we would consider GaN adoption in the luxury flagship models from these three leading players, Samsung, Huawei, and Apple. So this will bring me to my final slide, where we expect a great market dominance of consumer fast charging products over the next 5 years. Meanwhile, of course, several GaN companies such as EPC, Transform, have also achieved the automotive qualification, and GaN systems is also on the way. And there's a tremendous effort for development of GaN in the 48-volt DC-DC in the EV/HEV segment in collaboration with the tier 1s such as Valeo or Continental. So we can say that starting from 2023-24, we expect a takeoff in the automotive market, which will also then followed by the industrial segments, such as the data centers or the UPS. So these slides actually are extracted from our annually updated report, which is called Power GaN. which is published recently. So as I mentioned at the beginning, you will find a wide report collection in our activity covering both the established and the emerging compound semiconductor substrates. But in addition, I would like to note that since Q4 2019, we offer a new product called Compound Semiconductor Monitor Service, including the quarterly updated market data on silicon carbide and gallium nitride, power devices, and also the wafer and the epi-wafer markets. So this monitor is already available. And actually, following the entry of GaN devices in the high-volume consumer fast chargers and the silicon devices in the EV/HEV market, the market is rapidly changing, and we think that it needs to be analyzed quite frequently. So in this monitor, we also give a technological split of the market depending on the device technology, the substrate type or substrate size, as well as a detailed overview and market shares of the key players in both of these markets. And in the next quarters, we are adding gallium nitride and gallium arsenide in RF, and gallium arsenide and indium phosphide for photonic markets in our quarterly updated monitor service. So with this, I would like to thank you for your attention, and I will be happy to answer your questions.
Thank you very much, Yazgi, for this exhaustive overview of the GaN market. Now let's continue with Elena Barbarini, Head of Devices Department at System Plus Consulting. Elena, it's your turn.
Thank you, David. So hello, everybody. My presentation will be more oriented on technology and cost overview of the latest GaN power devices, and has already introduced some implementation of the device itself on the latest commercial devices. So just to have an overview, but actually it's already presented this slide. The market of GaN has now not really the market, but development of GaN has now already 10 years, but actually in the latest 3 years, we saw a really booming of new players entering this market, and finally some commercial applications such as the fast chargers. So if we have a look of the commercially available GaN devices, so actually all the devices we can easily buy, we see that there are two main groups of device according to the voltage application. So the low part, the low voltages market, it's mainly taken by EPC, and there are some other players that propose their device. While in the medium voltage market, so 600, between 600 and 750, we have a lot of players that propose their device. So here we see that actually it's in this area that we have different options in terms of design of the device and packaging of, for example, of the devices. So in my presentation, I will focus on the 600 and up to 750 volts devices. So if we have a look to the supply chain, actually it's interesting for us to understand the cost of fabrication. The device supply chain up to now, it's really it's full of players. While for example, for silicon carbide, it's quite linear. We have a few players able to do the epitaxy and to do the fabs. For GaN, we have a lot of players that actually enter the market even if they don't have the fab. So a lot of players that just propose at the design of their device, and then they use confirm the fabs to make the epitaxy of the device and actually the active device itself. So here you can see actually that the main fabs that they propose their services to do epitaxy and front end, TSMC, Epsilix Fab, and Fujitsu. And then we have other players like Infineon, Panasonic, Texas Instruments, that actually they use also their internal fab. If we have, why actually we are interested in GaN? Because actually GaN propose and enter the market thanks to their good performances and has main competitors in the range, always in the range of 600, 650 volts, the main competitors of super junction MOSFET. If we have a look about to the performances, the figure of merit of the latest devices proposed on the market, we see how the amelioration trends of GaN devices is going really fast. In the latest year, we have a lot of new proposals for GaN players. Anyway, I want to highlight that the research and investment on superjunction MOSFET, so silicon superjunction MOSFET, is continue, and player didn't stop their design and the offer of new products. Because actually, in terms of cost of device, silicon is still competitive, so that's why the development it's not finished. So we see that GaN it's really interesting, but it needs to be improved, especially in terms of cost. And actually, the challenges that we have in a GaN device that also imply a multitude of different solutions proposed by the different manufacturers can be listed in three axes. So the first challenge of a GaN device is the epitaxy itself. So we will see in actually my presentation I will focus on a GaNon silicon device and GaNon Sapphire device, but the epitaxy it's the main point of this device because actually of the latest mismatch between gallium nitride and silicon, and actually gallium nitride and all the substrate that we can have. Second problem is the normally on factor. So the design of the transistor itself, GaN, so actually it's normally on. But players have to find a solution to solve this problem and to have a normally off device. There are two main designs which we can find on the market. It's the cascode solution and the enhanced mode design. So here in the slide you have some player, for example, Transform propose a cascode power integration. It's a cascode design on GaNon Sapphire. And other players like Infineon, Hexagon, EPC, they propose their enhanced mode solution. So the main difference is the design itself of the gate, actually the two-dimensional electron gas part, and this can have an impact in the final packaging, in the design itself, the designs, but also in the packaging itself. And so the third point. The third challenge of GaN devices is the packaging itself. There is not one standard packaging up to now. Any player, according to the design of their devices and also the integration itself in the final solution, propose different solution of packaging. So we can have monolithic design. We can have a single die design, cascode, external drive, internal driver. So we will see these differences. So if we start with the first challenging, so the epitaxy. So the main problem, as I say, is the mismatch. Actually, GaN can be grown on silicon, sapphire, silicon carbide, and obviously GaN. But why the product that we have found now in the market are on silicon and sapphire? Mainly because of the cost of the epitaxy itself. If we have an epitaxy of GaN on GaN, we have less problem of mismatch. but at this moment, the cost of the substrate in GaN, it's too much to be implemented by integrator and to be accepted in a final cost of a device. So what's interesting for us actually is the first two type of epitaxy structures, of epitaxy device and substrate that we've seen in this slide, so the GaN on silicon and the GaN on Sapphire. Even if the Sapphire is a bit more expensive, the substrate, than on silicon, the fact that we have less mismatch allows us to have a shorter and a thinner epitaxy, and so a bit more cheaper. Why we focus on epitaxy? Because actually, so if you have a look to the cost of a GaN on silicon amp, we see that the epitaxy impact has a big impact on the final cost of the device. So the second challenge is the design itself of the die. So what I want to present here is a comparison of cost structure of the wafer and the die according to the design itself. So here I show you actually five die that can have a PN gate design, normally on, gate injection, thin PL-GaN barrier, and normally off on Sapphire. So here you see that the epitaxy is still the part that has a main impact on the final cost of the device. And then you have the front side, back side, and yield losses that are still higher comparing to silicon devices. So according to your need, you can choose one or other devices. So you need to always to have a trend between the performances and the cost itself of the die. The third challenge is the packaging. So actually, in the integration, we can find three types of integration of devices. We can have the option to have a discrete, so packaged discrete device and the external driver. That means that the integrator should choose his discrete and then his external driver to implement in a solution. The second option, so that means actually two devices in their design. The second option is the multi-chip integration, so having in the same packaging the GaN device with the driver. This is proposed by Texas and Power Integration. And the third option is the monolithic integration. What we call monolithic is to have the component and the IC on the same surface of a die. And then, obviously, these die are packaged or bare die. So these solutions are proposed by Navitas and EPC. So in terms of packaging, so these three solutions can be packaged in different way. Again, up to now, there is no one standard solution. We can have, we saw standard TO220 packaging up to wafer level packaging from EPC. The choice of packaging really depends on the application. And considering that linked between the GaN die manufacturer or designer and the integrator is really strong, up to now every designer works with integration to choose the best solution in terms of packaging.
Elena, we cannot hear you anymore. Are you there? Okay, sorry, we have a small technical problem. We'll be back in 1 minute. Sorry, we had a phone problem. Elena will be back in a few minutes.
Hello. So I'm sorry, actually the line just fell down. So I will continue my presentation. I'm really sorry about this technical problem. So what I was saying is that the packaging also has an impact on the final cost of the device. Here in this slide, you see an analysis of this impact. The first three devices that I show here, you have an enhanced mode device packaged in mainly standard. Let's call standard packaging. Actually, the first one is not really standard. It's a PC embedded device from GaN Systems, and then you have the two solution with standard packaging and single die without actual driver. The fourth option is the cascade mode. So in that case, we have to consider the integration of a MOSFET inside the packaging. And then we have the three last design that are devices with integrated driver that can be in the same package, so die external, but in the same package, or on the same monolithic solution. So here we see that usually the die with integrated driver are a bit more expensive than the component without driver. But again, this is a choice that has to be made in terms of what they want by the integrator. So if we come back and to the actual devices that we have found on the market, so commercial devices, in particular the fast wall chargers, we have seen that now we have two main trends. We have a lot of players that use Navitas device and a lot of players that use power integration devices. There is a battle between these two GaN die provider to integrate their solution in the fast wall chargers. And if we have a look about the link between the power of the charger and the volume of charger itself, we see that up to 50 watt, the GaN solution already gives some advantages in terms of volume of the charger, so implementation of the die inside the packaging. Above 50 watt, we have only GaN solution. How they are integrated, this device? So first of all, I want to highlight the two type of component that we found in wall chargers, so power integration and Navitas. I selected these two devices, power integration, actually both power integration and Navitas propose a different solution integrated in wall chargers, but I choose this one. So the main difference is first of all the type of substrate. Navitas propose GaN on silicon, while power integration propose GaN on Sapphire. And we have also the design and the integration. So power integration is a cascade, Navitas is an enhanced mode, integration it's a multi-chip and monolithic. But actually both are integrated in wall chargers. and up to now, both they give good performances in all the chargers. If we have a look about so the Oppo, Etsky presented the Oppo, so actually the first charger offer with the smartphone. What I want to highlight here actually is the solution, the changing of solution, the shifting of solution from silicon to GaN. So here I compare the Oppo X17 that has a power integration die, a power integration component with silicon die, it's a lateral DMOS, and the Oppo Reno Ace that propose also a power integration component with the GaN. But the solution has a package, multi-chip packaging, so the driver is integrated. But here we see that changing from 50 watts to 65 watts, so the GaN, so the component with GaN give more power. The die is much more smaller than silicon, but because it's cascode, they had to introduce the MOSFET inside the packaging. So that was my last slide for the technology and cost overview. So I will give back the talk to David, and thank you to everybody.
Thanks a lot, Elena, for your in-depth presentation. So the last presentation will be made by Nicolas Parent, co-founder and CEO of Nomade. It's about the patent side of the GaN market. Nicolas, it's your turn.
Yes, thank you, David, for the introduction, and hello, everybody. So at Nomade, we have investigated the patent landscape related to GaN technology for power electronics. We have identified more than 9,000 patents published worldwide. And these patents relate to AP wafers, power devices, device integration, circuitry, and packaging for all function, switch, converter, etc., and for all applications, power supply, fast charging, EV, HEV. The time evolution of patent publication shows two waves of patent publications, and since 2015 we have reached a plateau, and the peak in 2017 results mainly from numerous Chinese players, and this IP trend may reflect technology maturity. Indeed, a lot of patents now exist in the whole of value chain, from AP wafer and power devices to operating methods, device integration, and packaging. And on the other hand, market leaders with strong enforceable patents are present, and also more and more newcomers are entering the IP landscape. So this bar graph shows the main patent assignees according to the number of their patent families related to power GaN. And you can see that all power electronics market players are present. And among them, the main patent assignee is Infineon, followed by Toshiba, Fuji Electric, Renesas, Sanken, ROM, Onsemi, Texas Instruments, and Mitsubishi Electric. And today, Panasonic, Fujitsu, Furukawa, Sumitomo, and Sharp have an important IP portfolio because they were pioneers in GaN power patents. And also, among the GaN pure players supplying commercial GaN power devices, Transform is by far the main patent holder, ahead of GaN System, EPC, Navitas, Hexagon, or this IC. Now, this picture represents the entrance periods of main patent assignee in the power GaN patent landscape and their current patenting activity. So at the top, there are the IP players with decreasing or no longer filings of new inventions or new priority patents the last years. In the middle are the IP players showing steady or increasing patenting activity. Players still active in terms of new invention. And at the bottom right, there are the new entrants in the patent landscape. These new entrants have filed patents in 2016 or after. Some pioneers in power GaN patents, such as Furikawa Electric, Sumitomo Electric, and Sharp, have decreased their patent filing since 2015. And contrary to Panasonic or Fujitsu, which slightly maintain their IP activity. Also, we can note that Koreans are the missing players in the current patent landscape because Samsung Electronics, Samsung Electromechanics, LG Electronics, Inotech, and Seoul Semiconductor have strongly went down their IP activity after patenting period between 2010 and 2015. Meanwhile, a second wave of companies has entered the power GaN patent landscape between 2010 and 2015, and a lot of them are still active in terms of patent filings. And currently, most of power electronics players are intensifying their patenting activity, and especially Infineon, Toshiba, Sanken, Fuji Electric, Renesas, and Onsemi. And also, certain players are enlarging the geographical coverage of their patent portfolio by extending their priority patents, mainly in Europe and China. And this company showing this hybrid strategy of patent extension are, for example, Infineon, Transform, EPC, Power Integration, Texas Instruments, Intel, Navitas, Toshiba, and Renesas. And then the last 3 years, more and more newcomers are entering the patent landscape with first patent publication related to power GaN. And as new entrants, there are, for example, GaN startups, Navitas, Hexagan, Cambridge Electronics, the Chinese GaN Power, and InnoScience. There are also substrate providers, Chromis, Airwater, or Zinc Semiconductor. We have power management supplier Jalog, and also some foundries such as Founder Microelectronics, the Chinese, Sinopower, iWafer, Singwi, and Nuvoton. And also, we recently observed first power GaN patents filed by Nissan, Renault, Ela, Midea, and Velodyne, Nidar. This graph represents what we call IP leadership of main patent assignee. So the vertical axis represents the number of granted patents, and the horizontal axis represents the number of pending patent application. So in just a few years, Infineon and Transform have reached the strongest IP positions in the power GaN patent landscape. And today, this offers them the capability to limit the activity of competitors. Infineon definitely has the strongest IP portfolio, thanks to the acquisition of international rectifier, but also thanks to numerous enforceable patents, a lot of pending patent applications, and fundamental patents covering all the value chain from AP wafers and power devices to operating methods, circuitry, and packaging. And we think that Infineon will likely maintain its IP leadership for a long time. And Transform has become a major force in the power GaN patent landscape, and it is currently the main IP challenger in power GaN. Transform holds a broad patent portfolio comprising fundamental patents in all the value chain, ranging from AP wafers, power devices, circuitry, and packaging. And the company owns numerous enforceable patents, many in the US. But Transform slowed down its IP activity the last 3 years in terms of new invention, but it continues to expand its priority patents with a particular interest for China and Taiwan. And also Furukawa and Panasonic, which have a good IP position, have already leveraged their good IP position by licensing their patents to Transform and Infineon. And other players which have reinforced their IP position the last years are, for example, Toshiba, Intel, Renesas, EPC, Power Integration, Onsemi, Toyota, Texas Instruments, Sanken, TSMC, and Toyota Gose. Now, if we have a look at the GaN silicon and GaN Sapphire technologies for power application, concerning the GaN silicon technology, only 10% of power GaN patents explicitly mention the silicon as a preferred substrate. So the GaN silicon patent landscape is characterized by the presence of numerous GaN pure players, such as Transform, EPC, GaN System, Navitas, Hexagon, this IC, Cambridge Electronics. And currently, the most active players in terms of patent filings that clearly mention the GaN silicon technology are Infineon, Intel, Toshiba, and Texas Instruments. Regarding new entrants in the power GaN patents for GaN silicon technology, China has made an impressive move into this landscape with numerous new entrants since 2017. Mainly, we can mention Founder, Microelectronics IC, and InnoScience. And other noticeable new entrants are Renault, Airwater, MMOS Semiconductor, Delta Electronics, Vishay, and Epistar. And the last year, we observed a growing patenting activity for power GaN system-on-chip solution, in particular with patents of Infineon, Intel, and Navitas. Concerning vertical power devices, yes, several GaN players hold patents on vertical power devices using GaN on silicon technology. And for example, Fuji Electric, Vishay, Renesas, ST Microelectronics, and Renault develop such IP. And also, for power IC, some players such as Intel, IBM, TSMC, etc., develop IP related to GaN on SOI substrate. Now, regarding the GaN on silicon, the GaN on Sapphire for power electronics, we have identified more than 80 inventions related to GaN on Sapphire technology for power application. And power integration is the best known player, but only 2 of its patents explicitly mention the Sapphire as substrate. And numerous other players have also developed IP related to GaN on Sapphire power devices. Most of patent applicants justify the use of Sapphire substrate to reduce the manufacturing costs of the chip, for example, with power deck, and also to leverage their epitaxial know-how, like Seoul Semiconductor. So among the IP players having patents on GaN on Sapphire for power electronics, there is PowerDeck with patents on GaN polarized superjunction transistor and fast charging system. There is Seoul Semiconductor with patents related to epitaxial lateral overgrowth, Schottky diodes, normally off transistor and vertical transistor. There is also HRL Laboratories with patents on monolithically integrated power converter using a Sapphire substrate. And also we have Fujitsu and Alpha and Omega with patents in which the Sapphire substrate is removed after the formation of the stack in order to solve the problem of the weak thermal conductivity of the Sapphire. And finally, we have also the Arizona State University, which recently developed a patent on high voltage aluminum nitride by Schottky diode on Sapphire. And just I will close my presentation with this map of a very important player and unavoidable IP players for all those involved in power GaN. So thank you very much for your attention.
Thank you very much, Nicolas. So we will now end the webcast with the Q&A session. We will answer a few questions as we are running out of time. So the first question is for Yole Développement and SG. How do you see the development of the GaN power business supply chain in the next years?
So, thank you for the question. I can say that as of today, so we are seeing several, let's say, developments, several business models in the GaN power business. So the first one is, as I have mentioned, and as Nicolas and Elena have also shown, it's from the innovative startup companies who are using the foundries. And in the last years, we have seen the arrival of new GaN power and new fabless players such as GaN Power, Tagortec, or Wise Integration. And I think it will also continue to increase because there is still a lot of technological developments are possible. And in the foundry business, we also see new foundries such as iGaN or Sanan IC or Innoscience from China. So this will also help these actors to ramp up quickly. And the second business model that we are seeing is also the power module and a discrete power device manufacturer. So it would be like Infineon, ST Microelectronics, or onsemi. So we have seen from the presentation of Nicolas that Infineon is also strengthening the IP position on GaN. So basically, these players are getting ready on the GaN product portfolio. But we can say that one of the business models that I'm seeing interesting is the power management players, the players such as Power Integrations or Texas Instruments. So we have seen in the case of Power Integrations, they have combined their know-how on the GaN HEMT and also their, let's say, strong background on the gate driver technology. And in a way, this facilitated also the usage of these devices by the end users. So it's quite a clever way actually to get the market acceptance at their already known clients. And the fourth business model I would see would be if the GaN on Sapphire technology gets more mainstream, the many LED manufacturers with the high volume capacity, MOCVD capacity, can also benefit from this. So here, of course, it's important to note that the IP and the know-how of GaN power devices is really, really important. So they would also need long time to develop this.
Thank you, Ezgi. One question for Elena. So do you see any trends in packaging integration, and do you think there will be a design win?
Thank you for the question. So actually now the packaging market, it's really wide. We have different solutions. What we have seen is that in consumer application, so in the use of dye on smartphone, the main trend is to integrate the driver. So we can see that a trend can be the integration of driver in the same packaging. That's mainly to help the integrator to keep the same design of charger. For other applications, for low voltage application, the trend is more on simple devices, so mainly monolithic single device and wafer level packaging or embedded die. So I don't think now there is one design win, because there are other applications that can be where GaN can enter. So in that case, for sure we will see this other type of packaging. But for the two applications that we have seen now, I mainly integrated the driver or completely single device without particular packaging. Thank you.
Thank you, Elena. And we'll have a last question for Nicolas from NUMAID.
Yep.
Nicolas, do you see within the current patent activity a growing interest of the EV and HEV application with GaN?
Okay, so I would say yes. There is a few power GaN patents that clearly mention automotive application. Today, there are about 100 patents which clearly mention electric vehicle as a main application. And the number is increasing. And also, we have seen more and more automotive players entering the power GaN patent landscape the last few years. Today, the main patent holders targeting automotive application for GaN technology are Toyota, Denso, Bosch, Fujitsu. We have also Furukawa Electric, Transform, and ROM. And more recently, we have seen first power GaN patents filed by other automotive players, such as Renault, Nissan, Hella, Magna, China Motor. So I would say yes. In patents as well, we observe a growing interest in GaN technology for EV, HEV application.
Thank you very much, Nicolas. So feel free to share this presentation to colleagues, and if you still have some question afterward the webcast, you have on the presentation our contact details. Feel free to send us an email with some questions. So the webcast is now over. Let me remind you that tomorrow you will receive an email with the link to the recorded session, and that you can get more information about our reports on our website, i-micronews.com, and also our brand new offer on quarterly monitors that we have on the Compound Semi, but also other thematics. Thank you very much, everybody, for joining us today, and have a very good end of day. Goodbye.